Have you ever just stared at a physics problem and had no idea where to even begin? Yeah, we've all been there. Today, we're going to walk through a classic mechanics problem together. But the goal isn't just to find the answer, it's to build up your problem-solving confidence. Let's dive in.
So here's our game plan. First, we'll break the problem down into simple parts. Then we'll find the one key equation that connects everything. From there, it's a straight shot to solving for velocity and distance, answering the questions, and finally, reviewing the core physics. It's our roadmap, so we won't get lost.
All right, before you even think about touching a calculator or writing an equation, the single most important step is to really understand the quest. What information are we actually given, and what exactly are we trying to find? Let's break it down.
Okay, so here's the problem itself. I know, at first glance, it looks a little intimidating with all those variables and the cosine thing. But trust me, every part of this is just a clue. We're going to go through it piece by piece. Don't worry. This table is our best friend for getting organized. On the left, you see everything the problem just handed us. And notice this is absolutely crucial, the initial conditions. At time 0, the particle starts moving. That means its initial velocity is 0 and its initial position is 0. On the right, those are our goals. This gives us a crystal clear map from where we are to where we need to be.
So, we have a force, and that force is changing over time. And we need to find out about the particle's motion, its velocity, its distance. To build a bridge between the world of forces and the world of motion, we need a fundamental law of physics. We need a compass to guide us.
And that compass is, of course, Newton's second law. This is the absolute bedrock of mechanics. We're going to use the calculus version here, F equals m times dv over dt, because it's the perfect tool. It directly connects the force we know to the change in velocity we want to find.
All right, compass in hand, or we're ready to start. The first leg of our journey is to use Newton's law to figure out an equation for the particle's velocity at any given moment.
Let's walk through this. First, we just set up our equation by putting our specific force into Newton's law. Next, a little bit of algebra to get the dv on one side and dt on the other. And now, the magic step. We integrate. Integrating cosine gives us sine. But wait, that's a general solution. We need the one for our particle. And that's where the initial conditions come in. We know at t equals 0, v equals 0. When you plug that in, you find the constant of integration is just 0. And just like that, we have our final specific equation for velocity.
So we just went from force to velocity. Now we're going to take the next step and go from velocity to distance. And here's the really cool part. We're going to use the exact same method. Once you get this pattern down, you realize just how powerful this technique is.
Okay, here we go again. We know that velocity is just the change in position over time, right? So v equals ds over dt. We just pop in the velocity equation we just found, separate our variables, and integrate one more time. The integral of sine is negative cosine. Then we use our other initial condition that the position is 0 at time 0 to solve for our new integration constant. And that leads us right to our final equation for the particle's distance.
All right, the heavy lifting is done. Seriously, we've derived our equations for velocity and distance at any time t. Now we are fully equipped to go back and just knock out the 3 questions from the original problem.
So, first up, the particle speeds up, then it slows down. How long does that take until it comes to a complete stop for the very first time?
The key here is translating words into math. The word stops just means one thing, velocity is 0. So we take our big velocity equation and set the whole thing equal to 0. Now that first part is just a bunch of constants, so it can't be 0. That means the only way for this to work is if the sine of omega t is 0. And when is the sine function 0? Well, it's 0, at pi, at 2 pi, and so on. Since the particle starts at time 0, the first time it stops after starting must be when omega t equals pi.
And with a tiny bit of algebra, we solve for t. And there's our first answer. Pi divided by omega. That's how long it was moving.
Okay, next question. We know how long it moved, but how far did it actually go in that time?
This is where our previous work makes life so easy. We just take the time we just found, and we plug it straight into our distance equation. So omega times pi over omega is just pi. We get a cosine of pi inside the parentheses. And we know from the unit circle that the cosine of pi is -1. So 1 minus -1, that just becomes 2.
And that's our second answer. The total distance is 2 times f0 all over m omega squared. 2 down, 1 to go.
Last question.
During this whole trip, from starting at rest to stopping for the first time, what was its top speed? What was its maximum velocity?
To figure this out, let's just look at our velocity equation. It's a chunk of constants multiplied by a sine function. Well, the velocity is going to be at its absolute biggest when that sine part is at its absolute biggest. And what's the maximum value a sine function can ever have? It's just 1.
So the maximum velocity is simply that group of constants out in front, f naught divided by m omega. And that's it. We did it. We've completely solved all 3 parts of the problem.
Now, getting the answers is great, but the real win here, the thing you should really take away, isn't the final numbers. It's the method. Let's quickly review the key concepts so you can put them in your own toolkit for the next problem you face.
Okay, here are the big takeaways. Number 1, always start with the fundamental law, F equals m. 2, remember that integration is how you climb the ladder from acceleration to velocity and from velocity to position. 3, never ever forget your initial conditions. They're what make your general solution specific to the problem. And 4, practice turning the words of a problem, like stops, into the language of math, like v equals 0.
And hey, just as important, here are a few common traps to watch out for. It is so easy to forget that little plus c when you integrate, or to mix up the integral of sine and cosine. Also, read carefully. Paying attention to a word like first is huge. And finally, don't mix up when something is 0 versus when it's at a maximum. Avoiding these little mistakes will save you a ton of headaches.
And to leave you with a little challenge, what if that starting force was a sine function instead of a cosine? What would that mean for the particle right at the very beginning, at t equals 0? How would that change our answers? Give it a shot using the exact same method we used today. It's a great way to make sure you've really got this down. Thanks for joining me.